Hello, welcome my people, welcome my friends to discuss a little bit about basic inorganic chemistry. And this is a lecture one which discuss critical the chemistry of hydrogen. Our course code is CH1204 in university, and my name is Anthony Bairo. Welcome so much. Be well and be comfortable to listen this course, and you can have a notebook to take note for some tips that you can think that will be important for you to understand this course. Welcome very much. Now, okay, let us start to discuss a little bit about hydrogen. Actually, while we are discussing hydrogen has some unique properties, and the main unique properties is that it does not belong in any group or in the periodic table. Also, it has three isotopes which differ so much. Also, has a unique chemistry compared to other elements. Okay, come on. Now, where actually can we find hydrogen? Hydrogen can be found in water in combined form, actually, and in hydrocarbons and carbohydrates. But in all organic matters, there is hydrogen, which can be combined actually with carbon, nitrogen, or oxygen, like protein, carbohydrates, and lipids. Also, this was the first element in the periodic table which have the atomic number of 1, and its mass number is actually 1.008 atomic mass unit. And the nucleus of hydrogen contain only one proton, but there is no neutron. This is a basic knowledge about hydrogen. And this has the tendency of losing one electron and becoming proton, which is hydrogen plus. It bears electronegative and electropositive characters. We are going to see here. I've said it can lose one electron, but later you can see also it can have a ability to receive one electron and become hydride. This is a proton, and later on you're going to see what is a hydride. Okay, now we are going to see there are some similarities with group 1 element. That's why some people are thinking that hydrogen is belonging to group 1 element. Now, hydrogen has one electron alpha, most shell like those alkali metals like sodium, potassium, cesium, and lithium. Also, alkali metals has the tendency to lose one electron from outer shells, similar to hydrogen that forms proton. Also, valence of hydrogen and alkali is 1. Alkali metals is 1, and actually you can see hydrogen has the combining power of 1. Combining power for an element is what we're calling a valence, and so hydrogen has such behavior. And hydrogen forms stable oxide like water, and this also peroxides, and this is similar to alkali metals. Also, we have sodium oxide, which is similar to water. We can say it is the analog of water because it forms two metal atoms and a single oxygen like water, having two hydrogens and oxygen. Okay, now what are the difference between of hydrogen comparable to group 1 elements? Hydrogen has higher energy, we can say higher ionization energy compared to alkali metals. Also has very small size compared to alkali metals. These 2 points makes hydrogen being different from group 1 elements. Now let us see some people who have been portrayed that hydrogen being group 17 element, which known as halogens. Hydrogen has the behavior of gaining one electron and forming hydride, which is H minus. Like halogens forms chloride, forms chloride, like chlorine forms chloride, and like fluoride forms fluoride. Also bromine from bromine. So from those examples, you can say that hydrogen has some behavior compared to halogens. The ionization energy of hydrogen is comparable to halogens, means the ionization potential of hydrogen is near the same to that of halogens. Also, hydrogen molecules forms diatomic halogens. We can say the atomic compound or the atomic molecule like halogens. Example, fluoride. Fluorine combines with fluorine to form fluorine gas. Chlorine combines with chlorine to form chlorine gas. Similarly, hydrogen combines with hydrogen to form hydrogens, which is their hydrogen molecule, hydrogen gas, right? So that behavior makes it to be similar to halogens. Also, hydrogen forms hydride with carbon, like methane. And similarly, some halogens like chlorine forms chloride with carbon to form tetrachloromethane, like this one here you can see, similar to this one. Also, hydrogen in organic compounds can be substituted by halogens. So by saying that chloride can be in the place of hydrogen, here you can say also there is a similarity of hydrogen with halogens. Okay, now let us see what is the difference between hydrogen and halogens, because we've seen the similarities. Now, what is the main difference? The electron affinity of hydrogen is much higher than that of hydrogen. So the electron affinity of halogen, if it's higher compared to that of hydrogen, what do we mean? Is that the energy produced when halogen receiving electron is greater compared to that of hydrogen. This makes difference between hydrogen and halogens. Also, the hydride formed by hydrogen with the metals are much stronger electropositive. We can say are much stronger compounds compared to that forms with the halogens. Example: sodium hydride and calcium hydride are much stable hydrides compared to what we're calling it sodium chloride and calcium chlorides. So the hydride and chloride of strong electropositive metals are much different in terms of stability. That's what I can say. Those compounds formed by hydrogen with the electropositive metals are much stable compared to that formed with the electropositive metal with halides. Now, due to those behavior, we can say that hydrogen cannot be placed in group 7 element, hence being independent. Now, why can we say that hydrogen is unique in the periodic table? First of all, it's non-metal in group 1. So, it is a group 1 element by some properties, but is non-metal. While we know the group 1 element are metals. Also, it then formed more than one ion, which is plus and minus, which is plus 1 and minus 1. And the plus 1 is what we know it as proton, and eventually is stable. And we have also minus 1, which is known as hydride. Now, from there, we can start to see. We have discussed a little bit about hydrogen behavior and so forth. But now, let us turn back to a real sense of hydrogen, what we know. Now, let us study what is hydrogen gas, how we prepare it, and what are their uses. Actually, we should start with the preparation of hydrogen gas. In large scale or in industrial preparation, we are preparing it by reacting gaseous water with the propane. So propane reacts with the steam, we can say the gaseous water, to provide carbon monoxide and the hydrogen gas. Also, in other process, we're using coke, which is a hot coke with the water, which is gaseous water, also to get carbon monoxide and the hydrogen gas. Now, these are some preparations that we've seen here, but let us see what is the small quantity preparation of hydrogen gas that we have. Some people have been discussed or have been learned in ordinary level or in laboratory preparation, where we are using some experiments to prepare hydrogen in the laboratory. This is prepared by using granules of zinc. We are dissolving it in a dilute sulfuric acid, and this is the apparatus setup. Here we just placing sulfuric acid, which is dilute sulfuric acid, and this is a control valve which actually we are opening to allow sulfuric acid to enter, and here is the zinc granules. Then gas is produced and come into this side and being collected in this jar. So this is the basic preparation of hydrogen in the laboratory. But in real scenario, or you can say in an economic aspect, we cannot use this method to prepare hydrogen gas. What actually happens, we are using what we know it as electrolyzers, but you're going to see it well. Also, this is hydrogen gas can be produced by using this we can say these reactive metals. By using these reactive metals and dipping it in the pure water, then hydrogen can be also produced. But in a commercial way, we cannot also produce by this way. So in a commercial way or in large scale, we are producing it by using electrolysis method. Okay. Now, we've discussed a little bit about preparation of hydrogen. Now, hydrogen have been already prepared. How can we test it to know here is hydrogen? This is one of example. We say that a boy forgets a lab to label contents of 2 test tubes, and he wants to know actually which test tube has hydrogen and which has carbon dioxide, because all of them have similar physical properties, you can say similar observable properties like odorless, colorless, tasteless. Those are some observable and testable properties. But how can we actually know which test tube has hydrogen gas? Now, the main test that we can use is using it with a splint. We're just lighting a splint. Then after lighting it, we are passing on top of the test tube that have those gases. So the test tube having hydrogen gas will have a pop sound, and that test tube have carbon monoxide will actually not having a pop sound, will not burn, actually will stop, because carbon dioxide is somehow not combustible. We can say it's not combustible, but hydrogen gas is combustible, but have a violent combustion. That's what produce pop sound. You can say it explodes. Okay, now what are the physical properties of hydrogen? Why we are talking about the physical properties? Now let us look for those properties which are measurable and actually can be also visible, like colorless, odorless, tasteless, and lightest gas in terms of density and so forth. But what are the behaviors like this one, which is energy produced when heated, or when burned, when hydrogen burn, means when hydrogen reacts with oxygen, produce a lot of energy, and they produce that pop sound that we have been discussed in the previous slide. Now, these are some physical properties like melting point, boiling point, and so forth. These are very important to understand and very important to know. Now, let us turn back to see chemical properties of hydrogen. What actually could take place when hydrogen reacts with other elements? What will take place when hydrogen is subjected into particular conditions, and so forth? Now, we are saying hydrogen gas does not usually react with other chemicals at room temperature. That's very true. But at which condition now hydrogen reacts? When actually the activation energy is produced, is given to hydrogen, can react with oxygen, can react with some metals to provide some hydrates and some hydrogen oxide, which is not like water and so forth. But here we are really focusing on what is the main concept, or what is the main chemical property of hydrogen. Basically, the reactions of hydrogen are in two ways. Either it can receive electron to form hydride, or it can give electron, it can lose electron, by the way, and they provide and become hydrogen plus, which is proton. By another way, it can share electron to form a single covalent bond, like hydrogen, which is hydrogen gas, or in some cases hydrogen bromide, which is hydrogen bromide HBr. So this is one of the covalent compounds which are really formed by sharing of electrons. Now, after knowing that, the chemical properties and physical properties and so forth, let us know the uses of hydrogen. There are several uses of hydrogen, but it's very important to understand the chief usage of hydrogen. The first one is in Haber process, production of ammonia. Hydrogen reacts with nitrogen to produce ammonia, but still we are not consuming ammonia. Where ammonia is going? Ammonia is going to produce urea, to produce fertilizers, which is ammonium chloride and so forth. So, like NPK fertilizers are produced by ammonia. So, the main use of hydrogen is in production of ammonia, which in real application is used in production of fertilizers. The another application, hydrogen gas is used in energy production. Hydrogen gas used in fuel cells to produce electricity. But in addition point is that hydrogen are used in addition reactions. In organic reactions, we have some addition reactions. Example, we have some unsaturated alkanes. We need to provide saturated alkanes. So these saturated hydrocarbons, I'm very sorry, not saying saturated alkanes, we are saying we have unsaturated hydrocarbons, and we need to produce saturated hydrocarbons. We have to add hydrogen. We're using hydrogen with a catalyst, which is a nickel or platinum catalyst. We are converting unsaturated hydrocarbons, which are alkene or alkyne, into alkane, which are saturated hydrocarbons. Now, from there, let us go to isotopes of hydrogen as the main important part also to discuss. Hydrogen has three isotopes. The first one is protium, second one is deuterium, and another one is tritium. Protium has the mass number, we can say the molar mass of 1. Deuterium has a molar mass of 2. And tritium has the molar mass of 3. Now, we can say that we didn't focus on other isotopes of hydrogen for the previous studies of our curriculum. We just focused on the protium, which have the molar mass of 1. And I think many members are just knowing that hydrogen has a molar mass of 1. But why is that? Because the main abundance of hydrogen is ordinary hydrogen, which is protium having the molar mass of 1, which the percentage is 99.984%. So in nature, we just have a lot of hydrogen, which is ordinary, not other hydrogens. But the other percentage are for deuterium and tritium, which are very less significant to us. That's why we didn't discuss it. But in the scientific field, we need to discuss them if they'll be applicable in our real life of science. Now we have deuterium having a very little percent that we are seeing is 0.016. Also have tritium, which are very little percent. A very little percent. Okay, now let us go very straight to see what actually are these isotopes. We have, which is a protium. This one is protium, this is deuterium, and this is tritium. But here you have seen hydrogen. This is ordinary hydrogen, by the way. Now, we've discussed the isotopes. We know protium, we know deuterium, and we know tritium in terms of molar weight. And they have several numbers of neutrons and so forth. So, let us discuss now one of the isotopes known as deuterium. Deuterium has the molar mass of 2, and we have to discuss it because it will be applicable in our future use, basically in research purpose and in our experiments. Okay, deuterium can be obtained from heavy water, but this is still unknown. What is heavy water for now? Heavy water is the water that have hydrogen isotope having molar mass of 2. Or we can say water that has been made with the deuterium isotope is known as heavy water. Now, by dissolving sodium in it, you can produce sodium deuteroxide and the deuterium gas. Although in this method it's very difficult to recover the hydrogen, or we can say the deuterium gas that will be produced. Now, what are other alternative ways to produce deuterium? Because we have seen some challenges for the last slide, which is complete recovery is not possible. We are just recovering some deuterium gas, but not complete. Now, how can we actually recover other, we can say recover the remaining gases? Now, we have other ways. Here we're just using zinc to react it with the heavy water to produce deuterium gas. And also we're using tungsten with the heavy water to produce also deuterium gas. In other way, I can say that deuterium can be produced by those ways that have been discussed. But now you have deuterium. What are its chemical properties? it's very important to understand what will be the chemical properties are just like similar to those of ordinary hydrogen. Just when deuterium gas reacts with oxygen, produce heavy water, which is deuterium oxide. Okay. What are the action of halogens? It's very important to understand. While just discussing about the chemical properties, it's very important to focus on those on those groups of the periodic table. We've discussed how it reacts with oxygen to provide, in the previous slide, we discussed how it reacts with oxygen to provide heavy water. And here, how it reacts with halogens. That it reacts with hydrogens to produce these products. It's very important to memorize. Like here, provide deuterium chloride, and here also it provides deuterium fluoride. But it's very important to understand how to complete these reactions because they are very important to know. Okay, now we have to know the combination with nitrogen. How this deuterium combines with nitrogen in the presence of catalyst, similar like Haber process, where we are combining hydrogen with nitrogen to produce ammonia. Here, similarly, it appears like this. So, deuterium gas plus nitrogen provides deuterium ammonia. Now, let us go to see how it will combine with metals. As I can remind you, in the previous slide, also just discussed about the group of nitrogen that is known as a group 15. So it's very important while you asked to discuss about the chemical property of a substance to just try to react it with their groups in the periodic table. Like here, the combination with metals, we can see the reaction with metals to provide the deuteride. Like sodium reacts with deuterium, like the way sodium reacts with hydrogen, which is ordinary hydrogen, to provide sodium hydride. Now here it reacts with deuterium to provide the sodium deuteride. Okay, now and this sodium deuteride can be dissolved in water to provide a sodium hydroxide and the hydrogen within deuterium. Okay, now let us go to see again some reactions, which is addition reaction with unsaturated hydrocarbons, like addition of hydrogen in alkene to provide alkane. Now, similar deuterium can be added into alkane to provide some alkane which containing deuterium instead of hydrogen, which is known as ethylene deuteride when ethylene is added with the deuterium gas, and the presence of nickel catalyst provide ethylene deuteride. Okay, let us go again to see the exchange reaction. We're talking about the exchange reaction is that one atom is displaced with another one, but actually in some cases we can see that deuterium replace hydrogen. Why is it? Example, hydrogen and deuterium, just hydrogen replace deuterium from Hd, which is a hydrogen deuterium, which is isotopic hydrogen having two different isotopes. Okay, and ammonia reacts with deuterium from deuterium, ammonia, and the hydrogen. So deuterium just replace hydrogen. Similar to here just replace hydrogen, and here just replace hydrogen to form these products. Okay. Now from there we can start to discuss about heavy water. While speaking about the heavy water, we mean that water having deuterium isotope. This water had been discovered by somebody called Urey in 1932, and he showed that the ordinary water having a 1 part among 5,000 parts of heavy water. It means heavy water having 1 part, we can say in 5,000 molecules of water, there is 1 molecule of heavy water. Okay. Now, how can we prepare heavy water? Because in this situation, we cannot find heavy water. because it's only one part out of 5,000 is heavy water. How can we now prepare heavy water? Simply, it's very important to understand the electrolyte which could be used. Electrolyte is sodium hydroxide. Cathode is steel vessel, and anode is nickel sheet having holes. And in the preparation of heavy water, this simply you can say it is a electrolytic process which takes a little bit time. That's why it's called the prolonged electrolysis of water, which is an alkali. That's not a water, but that is an alkali. Okay, this is the model of electrolytic cell. It's very important also to understand it. How can you draw in simple diagram? In any way you can draw, but it's very important to label and to narrate what is cathode, what is anode, what's the electrolyte, and labeling. It's very important to know. Now let us start to discuss a little bit about the preparation of heavy water from the ordinary water. Now suppose you have ordinary water and you need to get heavy water. How can you do? At the first stage, you have to prepare electrolytic cells, and in this document I've shown there is 30 electrolytic cells are used in this step, and actually these cells are used in a production process. But one thing important to know is what are the input material, what are the conditions or requirements, and what is the output at the first stage. The input here is that 3% sodium hydroxide solution. This is a 3% weight by volume, means 3 grams dissolved in 100 ml, or in any ways that can describe that 3% sodium hydroxide in a particular volume, but this is a 3% weight by volume sodium hydroxide solution is the input material. And this process is carried for 72 hours when subjected into 110 volts direct current. While this process is going on, the volume is reduced by 1/6. We can say the volume is reduced by a fraction of 1/6 to the original volume, because some of the hydrogen are produced, some of oxygen is produced through electrolytic process, and after there, the whole solution will convert the water in it into 2.5% heavy water. So the level of heavy water in the ordinary water will be raised into 2.5%. Now at the second stage, here is only 6 electrolytic cells are used, and that 2% heavy water in it is raised to 12% heavy water. Why? The conditions are similar. What I mean, the potential difference, which is 110 volts, this is the same applied to the second stage, and the time is the same. Okay, at the third stage, what's important to know, that 12% is raised to 60% at the same condition like that's of in the stage 2. At the fourth stage, from 60 to 99% heavy water is obtained. So the level of heavy water in the solution is raised into 99%. And the fifth stage, here 99 is converted into nearly to 100% heavy water. Okay, but there's something important to understand, is that actually there are was alkali used, which is sodium hydroxide, in an electrolytic process. So what will be taken here is that the solution having 99% heavy, we can say heavy water, is electrolyzed to produce deuterium gas and oxygen gas, which later are going to burn to form heavy water, which is pure. So the point of electrolysis here is not going to be taken similar to those other stages. What is going to be done here is that the heavy water from the cell will be split into deuterium gas and the oxygen gas, and later on they're going to burn. They're going to react to form heavy water, which is D2O. Now, suppose you have heavy water in the beaker and the ordinary water in the beaker. In normal sense, or in the real situation, how can you distinguish heavy water and the ordinary water? Now, as you can see, the physical properties, both are colorless. Ordinary water and the heavy water colorless, tasteless and odorless liquids. Now, by using these other properties, which are also physical, but actually they can be well measured in a laboratory, you can distinguish heavy water from ordinary water. The main important thing to understand here is the density. As the name indicates, heavy water, what we meant is that the density of heavy water is great compared to that of ordinary water. So while you have been asked to distinguish heavy water and the ordinary water, the important procedure you have to take is to take the equivalent of heavy water and the ordinary water. Such equivalent of heavy water and ordinary water, if you take it to the balance, you're going to find that heavy water has a great weight compared to that of ordinary water. That's why the important thing to know is the density, because the density of ordinary water is H2O is 0.997 gram per centimeter cubic, while that of heavy water is 1.104 grams per centimeter cubic. So if we are going to measure 1 liter of this one, which is ordinary water, we're going to measure the beam balance or tonic balance or whatever. This one have a very less weight compared to this one, which could be easily distinguishable. Although other properties that we may going to use it, and it could give you answers, but this is the best property that can use and can give you readily results and at very quick moments, so you can have answer easily. Okay. Now let us see what are the chemical properties of heavy water, and while discussing about the chemical properties, should have to associate with either the composition or composition of the substance. So here we're just discussing the reactions of what the heavy water in real situation. Now here you can see these are some reactions. I think they are just similar like those of normal hydrogens, not much different. Okay. Another is a reaction with the metal oxides. I think also these are good examples that you can use. Reactions also with the non-metallic oxides, like this one we can use, and they could be good examples. I think also they're just similar like those of the normal hydrogen. We have some exchange reactions. Also they are much similar like those of the normal hydrogen. We have reactions with carbons, nitrites, phosphide, and acids. It's very important to memorize and to understand this because they are good examples to take while you're just describing the chemical properties of heavy water. Now, we have electrolysis process. How heavy water behaves in electrolysis. It's very similar to when pure water is subjected into electrolyzer. Just give hydrogen gas and oxygen gas. But important notion to understand here is that what can be asked is that suppose that we need to get deuterium gas. We need to get deuterium gas and we have ordinary water and we don't have sodium or any alkali metal or heavy metal in our laboratory. Now, what are the requirements can you give as the scientist to produce deuterium gas? What we have is only ordinary water. We don't have access to get heavy metal or alkali metal. Just tell us the requirements you need as a scientist while we are providing you ordinary water to give us a deuterium gas. So you must have to know what are the steps you can use from ordinary water to highlight the process that can produce heavy water. I mean those procedures to produce heavy water. Then from there, how can you use now that heavy water to produce deuterium gas? This is a one of chemical property, but it's very important thing to understand. How can you produce deuterium gas? Also we have deuterohydrates. What you're just describing about hydrates are these molecules which have been associated with the salt compounds, I can say with crystal in their crystallization forms, like sodium sulfate have some water molecules like this, heavy water. But similarly, as it happens with normal water, or we can say ordinary water, is similar as it appears with this heavy water, this deuterohydrates, like other hydrates. Now, as we've been described about hydrolysis reactions, similarly deuterolysis reactions takes place. So the heavy water reaction with the salts like aluminum chloride is known as deuterolysis. Similar as we discussed about hydrolysis reactions, that water reacts with a particular compound or any species, but we know it as hydrolysis. Now this is deuterolysis because this is a heavy water. And you can see the barium sulfide also reacts with water as well. So it's very important also to memorize these reactions. There are some significant biological and physiological effects of heavy water. And these are very important to understand because these are those make this cause to contain heavy water in our discussion. So it's very important to know their effects in living organisms and basically their toxic effects, and also it's very important to know their uses as well. So these points in these slides, or I can say these highlights in this slide, are describing their biological and physiological effects. Now, where we are using heavy water, because we've seen we're just producing heavy water, how we can produce heavy water, but we don't know how actually we are using it. Why is it usable? Now, heavy water is used in these experiments. Actually, is used as a neutron moderator. You really know that the fission of uranium, which is a reductive process, while we need to bring it to be slow, we need to make it slow. Actually, we are just solving the heavy water, so the nuclear reactor goes slow, not just rapidly going slow. Also, we've seen preparation of deuterium gas. In preparation of deuterium gas, we are just electrolyzing heavy water. In another uses is used as a test compound. Basically, when you're using heavy water medium instead of using ordinary water medium, we're just lowering the reaction. That's why there's some reactions like those reactions of phosphoric acids, which is oxalic acids, but these are inorganic acids. Inorganic acid reacts very rapidly, so we need to make them to be slow. If we need to make them to be slow, we have to react them in the heavy water medium instead of using ordinary water medium, where we can start the reaction mechanisms and so forth. So the reason to be used as a tracer compound, this is used to start those reactions which are very rapid. Now we're just making them to be slow. So this is the key uses of heavy water. Now from there we can see some behavior of hydrogen, and here is the property of hydrogen. This is not isomers of hydrogen. Basically, this is the isomers of hydrogen gas. Here you can say isomers of hydrogen gas instead of the isomers of hydrogen itself. You can say isomers of hydrogen gas. Okay, now what are the isomers of hydrogen gas? If you're saying isomers, we just mean the molecule having the similar molecular weight but having different structural formula, and the structural formula behaves intrinsically from the molecule, from the nuclei, not only from the arrangement maybe where the bonding is formed, whereas what as we're just discussing the organic chemistry. In organic chemistry, we're just saying the molecules have different structure but having the same molecular weight but different structures. But those molecules in terms of organic chemistry is somehow different the way we're just discussing about the hydrogen gas. Here what we're just describing is the nuclear property, or the structure of that hydrogen, or the behavior of that hydrogen comes to be different from another hydrogen. Thus we can come up with the isomer of hydrogen gas. Actually, we really know that hydrogen gas have one atom which is hydrogen and another atom which is hydrogen bonded together with covalent bond to form hydrogen gas. Now, the hydrogen itself has nuclear and electron, while another hydrogen similar have nuclear and electron. Now, once the bond is formed, one electron of one hydrogen is shared with another electron of another hydrogen. But nucleus are within the atoms. Those nucleus themselves, they are rotating, they are spinning, right? They are spinning, and the way they spin can be in same direction or can be in different direction. While a bond is formed, the nucleus itself is just spinning. So if the nucleus of one hydrogen is spinning in the clockwise direction, while another nucleus is spinning in the clockwise direction, so the spinning in the same direction gives also hydrogen isomer, while if the nuclei are spinning in opposite direction, while the one is spinning in counterclockwise direction, while another is spinning in the clockwise direction. This way, this gives a para hydrogen, which is another isomer. So basically, we have two isomers, which is ortho hydrogen and para hydrogen. Now, how these hydrogen isomers have different physical properties and how they behave in equilibrium mixture. Basically, ortho hydrogen can be converted into para hydrogen, no problem. But at which condition ortho hydrogen predominate? At which condition para hydrogen predominate? At 0 Kelvin, hydrogen contains mainly para hydrogen. It is more stable. So para hydrogen is more stable at 0 Kelvin. But at temperature, which is the liquefaction of air, the ratio of ortho and para are similar, 1:1. At room temperature, the ratio of ortho and to para hydrogen is 3:1. So you can see that at the room temperature, ortho hydrogen exceeding para hydrogen. Even at high temperature, the ratio of para hydrogen can never be more than 3:1. So you can see that the stability of ortho to para hydrogen is greater at the normal temperature. So you can say that ortho becomes stable at the room temperature, even at the higher temperature. Thus, it has been possible to get pure para hydrogen by cooling ordinary hydrogen gas to a very low temperature close to 20 K, but it is never possible to get sample of hydrogen containing more than 75% of ortho hydrogen. So you can see that even though we're just saying that the ortho hydrogen has a great percent, it's very possible to get para hydrogen by cooling ordinary hydrogen gas, but you really know that ordinary hydrogen gas has para and ortho. So we're just lowering temperature in order to obtain that para hydrogen. Okay, I think this is all about the isomers of hydrogen. Thank you very much, and this is the end of lecture 1.